Hello, we're going to look at example 10 now, and it says use plain vector algebra to show that the addition vector is commutative, right? And what does it mean to be commutative? So that means, let's say if we have vectors u, and we call them u sub 1, v sub 1, I'm sorry, u sub 2, and then vector v, and we call that, we have components v sub 1, v sub 2, what does it mean to be commutative? That means we need to show that u plus v is the same as vector v plus vector u. Now this may seem like really imperative and that this is true, especially after what we've shown, but in mathematics you just can't say, well, it's just so obvious. You have to have like a viable argument. So what we need to do is show that both of these are true. So we'll start with this guy, and what do we know about u to be? We know that u is the same as vector u is u1, u2, and vector v is v sub 1, v sub 2, right? And then we know from our vector algebra that we can represent this as u sub 1 plus v sub 1, and then this is u sub 2 plus v sub 2. Now inside of here, these are two addition numbers that we're going to be adding together. We know that numbers are commutative, right? That any, 1 plus 2 is the same as 2 plus 1, so we can write them in a different order. So this is, we can write this v sub 1 plus u sub 1, just switching them around, and the same thing here, v sub 2 plus u sub 2, right? And working backwards, since like we did up here, I can represent this as v sub 1, v sub 2, the vector v sub 1, v sub 2, plus u sub 1, u sub 2. And that is, we can write that as the vector v, and this is the vector u. So we've gone ahead and shown that this, that the addition, under addition, that is, too, think about it, would this be the same for subtraction? Can you show it the same? That'd be something for an exercise. It definitely is commutative. We're able to show that. So that's what we mean by commutative. So you can't just say, oh, well, it's obvious. You have to give some type of a more thorough argument, and that's what I did here. So let's look at another example. It says, example of use plain vector algebra to show that the zero vector, or the null vector, which has components 0, 0, that the identity element of is the identity element of the vector. What they mean by an identity is that if there's, when we have an identity and it's under addition, right? Under addition, we result the same thing. So what we want to show that that is the identity, then vector u plus the null vector is the same as the null vector plus u, and we end up with the same vector to begin with, right? And if we're going to show that this indeed comes out. So what is u sub 1 plus 0? That's, not u sub 1, but vector u, that's u sub 1, u sub 2 plus 0, 0. That would be the null vector, right? Then that I can put as 1 as u sub 1 plus 0, using our properties that we've shown in the previous video, plus 0, and what's this? That's just going to be u sub 1, u sub 2, right? And that is vector u, right? So what did we show? U sub 1 plus 0 does indeed yield the vector u. It's unchanged, right? Now let's go the other way. That would be 0, the null vector, plus u sub 1, u sub 2, all right, and 0 plus u sub 1, and 0 plus u sub 2, which is, again, u sub 1, u sub 2, and which is vector u. So we showed both ways that no matter what, that this is the identity that yields under addition. Would this be the same for subtraction? You have to think about it. That would be something for an exercise to see if you can show that, or maybe not. And then so the zero vector is the identity under addition. And I know this might seem obvious to you, but this is how we write a more thorough and rigorous argument, other than just saying that that it's obvious, it has to be true. So there you go. Thanks, guys.